C'est bon, quand tu veux.
Now, hello everybody. It's a pleasure today to welcome Olivier Absil from University of Liège in Belgium. Olivier is a researcher at FNRS, the National Research Institute. Olivier has done his thesis in Liège between 2001 and 2006, in common with the Observatoire de Paris. And the first time I met Olivier at this time, actually. Then he did a postdoc in Grenoble from 2006 and 2008, and then another postdoc in Liège between 2009 and 2012. And since 2013, he's a researcher at University of Belgium. Olivier is working mainly on, he has been working for 10 years in interferometry. And then in about 2009, he decided to go to work on coronagraphy, which is a technique that allows to make very, very detailed images at very, very high resolution of, for example, disks or exoplanets, in order to separate the different planets from the star. Today, I mean, this chorographic image, I will show us some very beautiful images, very amazing images of this technique. And today, coronagraphy is really one of the best techniques to image exoplanets and to separate from the stars. We'll see with him. He was granted the starting URC grant from 2013 and 2018, where he basically developed the concept of this coronagraph, which are vortex coronagraph, which were installed in the VLT and then also in the KEK and so in the LBT. So that was during his first grant until 2018. But he still was working on interferometry as he joined us for a study where we could, for the first time, observe a microlensing event and really distinguish the arcs of the images and see in real time the arc rotate around the star. So it was a very good, nice collaboration with Olivier. And he got a second URC grant, consolidator grant from 2019 up to today. And the idea of this grant was to implement a deep learning algorithm to study images of coronagraphs, and in particular for the instrument METIS that will be installed in the ELT and is responsible now for the development of the high resolution, high contrast part of this instrument. Voilà. So Olivier, it's up to you. Please go ahead.
Thank you for the introduction. Thank you for having me today, and nice to see so many people in the room today. So, as Arnaud said, I'm going to be talking today about the application of deep learning methods to the field of exoplanet high contrast imaging. And so, I mean, first to motivate my talk, I cannot resist showing this very impressive time lapse that shows the orbital motion of directly imaged planets over a period of about 12 years here. So this is one of the first directly imaged planetary system that features 4 giant planets orbiting at large distances from the host star, as you can see beyond the size of Saturn's orbit in our solar system. And I want to use this time lapse to highlight why we try to do direct imaging and why it's useful. So one of the first reasons is that it's one of the only techniques that allows you to detect and study the other parts of planetary systems. So these are parts of planetary systems that are usually not detectable with indirect methods that are more sensitive to the regions that are close in. Second thing, as you can figure out from this definition, is that we can study the evolutions and the dynamics of planetary systems. So just by looking at the planets move along the orbits, but also because with direct imaging, we have also the context of this evolution. We can see whether there are interactions with the surrounding planetary system, which can also host circumstellar dust. And this is especially the case at very young ages where the planets are still being formed. And direct imaging has a very important role to play to understand the conditions and the mechanism that leads to planet formation. So this is one example of an image of a young planetary system where you see a forming planet together with its disk of gas and dust in which it has been born. Finally, probably the most important reason why we want to do direct imaging is to separate the light from the planets, from the light of the host star, which allows us to present the light of those planets at the entrance of the spectrograph and then disperse the light of the planet and characterize what they are made of. But of course, high contrast imaging is a formidable challenge, as you probably all know. It's similar to trying to detect a firefly close to a lighthouse, except that unlike the lighthouse, the star never turns off. So we have to find ways to fight this high contrast scene, to fight this dynamic range in order to look for a very faint object close to a very bright one. And then in order to do so, we have a series of tools that we use. So first, we have to use large telescopes, which are typically ground-based telescopes, because this is where we can build the largest telescopes. Because they are ground-based, they need to be corrected for atmospheric turbulence. This is what Adaptive does. We then use coronagraphy to help manage the contrast between the two objects. And then we use a combination of observing strategies and image processing in order to try to disentangle this very complex image where you see a lot of structures that are linked to the diffraction pattern of the star across the atmosphere, across your telescope, across all the system that leads to the detection. And within this sea of speckle, you have to find the signature of your point-like source if you are looking for a planet. So just a single slide to highlight the hardware tools that we are using. So as I said, first, we have to use big telescopes. Second thing, to use adaptive optics, whose goal is to, using a wavefront sensor, measure in real time the shape of the wavefront that travel through the instrument and send commands to a deformable mirror that will change its shape in real time in order to correct for the deformation of the wavefront, in order to provide the flattest possible wavefront to the coronagraph so that it can produce the best and the sharpest possible images. And so finally, the third component is coronagraphy, which aims to basically block the stellar light in order to enhance the contrast between the star and the planet. And this can be done in various ways. The most common one these days is to use a focal plane mask that will just diffract the light of the star outside of the telescope pupil in order to block it in the downstream pupil plane. So regarding the observing strategies, we still have, when we do all this in terms of hardware, we still have a lot of stellar contamination in our images, and we still need to find a way to disentangle what comes from the star from what comes from circumstellar objects. And what you see here is the effect of field rotation. So what we can do is leverage the fact that the sky is rotating above us, and just to follow the field as it rotates because of just the rotation of our Earth. And the effect of that is that all the parts of the image that are linked to the telescope, so all the aberrations in the telescope, all the diffraction patterns are fixed because the telescope is just keep fixed with respect to the detector while the field is rotating. And so you see here the effect of the field rotation. And if you squint, you can see there are a couple of things that seems to be moving in the field, and these are actually actual objects that are in the field of view and that do rotate because of the field rotation. And so by doing so, you have been able to induce some diversity between the behavior of the speckles, which are basically linked to the diffraction pattern of your instrument. Of course, they do boil, they change their position slightly, they change their intensity, but you see that the global shape is remaining constant with respect to the actual astrophysical object that move in the field. Of course, the star is fixed at the center, and that's on the axis of the telescope all the time. So finally, when you have collected all your data, so you have a series of images. Basically, you have a video sequence of your star, and this is what is shown on the left. So you have a series of images across time. you can capture the contribution of the star by just taking the median of all these frames, because the planet will be moving in the field of view because of field rotation. They will not be captured by the median, while all the diffraction pattern that is fixed with respect to the detector will be captured by the median. And so by computing this median, you have a model of the response of your telescope to a single star. And you can subtract that from your data in order to further decrease the dynamic range between the starlight and the planets. So you basically enhance your contrast. And then you just need to derotate all the images, which is very simple because you know the rate of field rotation. This is your geometry, trigonometry. And then you stack all your images in order to get the final image where you can make detections. And so in practice, this is what it looks like. So this is, once again, your video sequence, your raw data. The first thing you do is to compute the median and subtract it from all the individual frames. This is what is shown here. So you see that most of the diffraction pattern that was present here is now gone because it was captured by the median and subtracted from the images. So this enhances the contrast value. And finally, when you derotate and stack up all the images, you start building up the signal. It's lagging a little bit, but you can see here, well, maybe it's going to play again, that as you stack the images more and more, you see that the signature of the planets become more and more obvious. There is 1, 2, 3, and even 4 if you look well, which are the 4 planets that I was showing in the first slide of my presentation. Okay, so despite all these complicated hardware and observing strategies and processing methods, the number of planets that have been detected by direct imaging is still very small. So there are a few dozens of directly imaged planets, which are here represented in a diagram that shows the mass versus the semi-major axis. And so what you see is that in blue, all these directly imaged planets, they are in a part of the parameter space that is not covered by any other method, which is of course something interesting, but also somewhat a problem because you would like to have overlap between direct imaging and other methods because combining methods is a way to learn more about planets. But one important point in this plot is that although directly imaged planets are few, they still represent a sizable fraction of all the planets that have been spectroscopically characterized. So the planets shown in field symbols here are the ones that have been characterized with spectroscopy. So you see there are a lot of transiting planets that have been characterized with spectroscopy, but still directly imaged planets represent a sizable fraction of this population of planets that have been characterized. And that's really what we want to do with direct imaging. So as I said, these planets are still few. And one of the reasons for that is that the part of the parameter space that we are sensitive to in terms of mass versus semi-major axis is quite limited. And it doesn't really correspond to the place and to the masses of the planet that planet formation model are telling you should be present in planetary systems. So we expect planets to form rather close to the snow lines, so typically between 2 to 5 AU or so for around the Sun-like star, and with masses typically not much larger than the mass of Jupiter. And this is this big population here of planets that have been detected by radial velocities or by transit. So you see here. And the part of the parameter space that we are sensitive to is right here and overlaps only marginally with the region where we expect planets to be formed. And even more so, what is not shown here is that our sensitivity is also limited by the fact that we are only sensitive to planets that are young enough so that they can still shine their own thermal emission. When they are old and cold, usually we don't detect them because detecting planets in reflected light is even much harder than detecting them in thermal emission. So what we would like to do with the next generation of instruments is to push this boundary of the detection limits towards closer separations, towards fainter planets in order to have a better overlap with radial velocities, which will give us a lot of information, additional information, because one of the problems with direct imaging is that usually we don't have access to the mass of the planets, and that creates a lot of degeneracies in the models that we try to fit to these planets, which is something that radial velocities can give us, of course. So in order to go deeper and fainter, one way to go is to build ever larger telescopes, and this is what is going to be done with the ELT. But still, even before doing that, there is still quite an untapped potential for current instruments to go deeper and closer to the star, and that's what I'm going to be talking about today. And I'm going to be talking about how machine learning can help in this endeavor. And so I will be covering three main parts where machine learning can help and provide new insight, which is improving the hardware performance of high-contrast imaging instruments, improve the software performance of image processing, and finally, I will say a few words about improving the scientific exploitation of the spectra that we extract. So as you have understood, this whole thing was the scope of my ERC project that ended about 1 month ago. And so this has been, of course, a big teamwork. So now I will just highlight some of the persons that have contributed to this project. So I'm starting with hardware performance. And I just want to highlight first the fact that the performance of current high-contrast imaging instrument is limited by not only by the fact that we do not correct perfectly atmospheric turbulence, but also by the fact that this correction is not exactly what we would like to do in practice. So what we have in an instrument is another system that corrects the wavefront at a specific position, which is a position of the wavefront sensor, while in practice we would like the wavefront to be as flat as possible inside the scientific instrument, which is a coronagraph. And so that you see that there is some optical path here and here that is not common between the wavefront sensor and the coronagraph, which means that what the wavefront sensor sees and what it does correct is not what we would like to correct if we want the coronagraph to see a flat wavefront. So these are called non-common path aberrations, and these are known to be one of the main limitations to the performance of high-contrast imaging instruments. And so it's been already, a decade or so to figure this out, and several strategies have been proposed in order to cope for that. So here, this is your traditional scheme for a coronagraphic instrument where you have light coming from a telescope. Part of the light is sent to the AO system. The rest is going to the instrument. Here, you would place your coronagraph using a focal plane and pupil plane in a different combination, putting different masks. And finally, you reach your detector. And so some various ways that have been proposed in the literature to measure and correct for non-common path aberrations are, for instance, to use a reflective focal plane mask that will just take part of the stellar light. The light that is usually blocked by the coronagraph will be sent to a camera in order to try to measure the quality of the wavefront at the position of the coronagraph. Another way with a coronagraph that do diffract the light outside of the telescope pupil, which is usually the case, which is blocked in the downstream pupil plane. You can also make this stop here effective and send the light toward the camera in order to measure the quality of the wavefront, once again at the position where it matters. But if you don't have the luxury to implement this kind of hardware solutions with an additional camera, you can also use the science camera itself to try to retrieve the actual amount of wavefront error that happens inside your coronagraphic instrument. And so this is called focal plane wavefront sensing. So one of the good things with this kind of technique is that you can retrofit any instrument because you always have a sensitive camera. You don't necessarily have access to, implementing new hardware, new cameras inside your instrument, but you always have access to your science camera. And you can use that in order to try to increase the correction efficiency of your adaptive optics system by measuring the wavefront exactly where it matters. So now there is a fundamental problem with this, is that when you get a measurement of your science image, you only have access to the intensity and not the phase of the light. And the reason why this is a problem is that when you have only access to the intensity and you try to reconstruct the aberrations, so these are phase aberrations in the upstream pupil plane that have created this PSF, you can show that there is an ambiguity In particular, if you decompose your wavefront in Zernike modes, you can show that the even Zernike modes can have an opposite sign and still produce the exact same PSF. That's what is shown here. So these two phase maps, they produce the exact same PSF. So that means that when you are faced with your measurement, real-time measurement in your science camera, you don't know which was the phase that created this particular pattern. But this is a well-known problem in optics. I mean, it's been known for a long time that if you induce some defocus in your optical system, you can leave this ambiguity. And this is what is called phase diversity, or that is used to retrieve the phase from focal plane images. So that has been used for decades in optics. But the problem is that when you do that, you lose half of your time because you have to spend half of your time defocusing your science camera, and you get basically useless images while you are doing that. And that's something that you don't want to do. You don't want to lose time on sky. So there are other ways to break this degeneracy. And one of them is to use an asymmetric pupil. You can show that if you induce some asymmetries in your pupil, you break the degeneracies between the sign of the even modes. So that's one thing. And another thing is that when you are using a vortex chronograph, so I've briefly introduced the fact that you put a phase mask in the focal plane to divert the light outside the telescope pupil. If you do that, you can also use the fact that the vector vortex phase mask induces different phase ramps to the different polarization, and if you split the polarization, you can also lift up the ambiguity. So these are two things that we have been looking at, and we have been looking at them in a new way, which is by using neural networks. So one of the reasons why we want to use neural networks is that usually when you get a focal plane image, whatever you have, phase diversity, asymmetric pupil, or vortex chronograph with this different polarization, you always have to use some kind of iterative technique in order to retrieve the phase that has led to these images. What you want to do with a neural network is to find a way to train a network to make instantaneous inference of the phase from the images. And so what you will do is to spend more time, more resources to train your neural network. But once it's trained, it is capable of doing instantaneous inference from the images that it gets. It can be phase diversity or asymmetric pupil or whatever. So the way it works is using supervised learning. And so here we start with some kind of knowledge of what we think the amount of wavefront error will be in our system. And so we draw at random some distribution of Zernike modes. So here these are the amplitude of Zernike modes starting from 0 to 100. So we draw them at random. We create a phase map that is driven by this randomization of our Zernike mode, and these are our labels. So our labels can be either the coefficients of the Zernike mode or the associated map that corresponds to this distribution of Zernike modes. So once we have that, we can propagate that through a simulator of our instrument to create the PSFs, in this case, in focus and out of focus for phase diversity. We do some pre-processing to have as realistic as possible data, and these are our training data. So basically what we do is to create pairs of images and labels that we can then feed to a neural network to learn the mapping between the focal plane images and the upstream pupil plane phase errors. And this is a typical architecture for a neural network that will do that task. So we are using convolutional neural networks that do use the structure of images in order to try to extract features in the images and progressively narrowing down the amount of information in the images through this bottleneck, and then decompressing them in order to create an output that is a phase map. Of course, at the start, the network is not trained, so that means that when you put something in the input, the output will not correspond to the amount of phase error in your pupil plane, but then you define a loss function that is basically the difference between your labels and what is the output of your neural network. So you basically compare the output with your labels, which can be either the full map or just the coefficients of the Zernike modes. And you compute this loss and you backpropagate it through your network in order to adjust the weights of all the neurons inside your neural network in order for the output to match as well as possible the labels that you have for your data set. Okay, so this is called supervised learning. And well, I mean, this is a pretty standard in deep learning these days. So does it work? So here what I'm showing is the amount of wavefront error that we have introduced as a function of the Zernike modes. So here low order modes, deep-tailed, focused, astigmatism, and so on, going to a higher order mode. And so these are the amount of wavefront errors that we have introduced. We're using some kind of power law that is more or less representative of what we think an optical system will provide. And now these are different inferences obtained with different networks that are trained in different ways. And so every time what I'm showing is the difference between what we have injected and what's the neural network's outputs as its most probable estimation of the Zernike coefficients. And so in red, it's using only in-focus images. And so in that case, you have this sign ambiguity, which means that all the even modes that are highlighted in green here cannot be retrieved. And so you see that indeed, while we can estimate and subtract the odd modes, the even modes, we cannot really constrain them at all. If you are using only the out of focus image, then you can break the degeneracy, but the accuracy is not very good because the light is more spread out on the detector. And finally, if you use the combination of in focus and out of focus images, then you can get a pretty decent job estimating all the modes with a quite good accuracy. And actually, in terms of accuracy, we have tested whether the neural network approaches the fundamental limits of wavefront sensing, and indeed, this is the fundamental limit limited by just photon noise, and we see that our estimations match quite well the fundamental limits, with here a trend to not approach the fundamental limit where we have a lot of signal. It's just because in that case we would have needed to train even more the neural network to reach the fundamental limit, which we do think that we could reach the fundamental limit if we trained even more the neural network. Okay, so now comes the question of what happens when we go on Sky, because all I've been presenting so far is just simulations, okay, using a simulator for our instrument to produce synthetic data and training the neural network based on synthetic data. So now what happens if you go on Sky is that you don't have labels anymore, because you don't know what is the status of your system, you don't know what are the aberrations when you observe on Sky, all the more that all the surrounding, the environment and the adaptive system and everything can also add more errors to your system. So basically, you cannot train anymore your neural network because you do not have your labels anymore. So one of the things that we can do, and we have tried to do, is the following. So using the output of the neural network, which in this case are Zernike coefficient, and inputting them into a simulator of our instrument. And this simulator needs to be differentiable. That means that we need to be able to backpropagate gradients through the whole system. And in that case, the simulator is producing images of what it thinks that these aberrations would create. And so in the end of the day, what we do is just compare the output of the simulators to the images that we get from the telescope. And so we can train the whole thing, so both adapting some of the parameters of the simulator and the parameters of our neural network, so that the output of the simulator, the reconstructed PSF, match as best as possible the input PSF. And so this is called unsupervised learning because we do not have. Okay. So for the sake of time, I will just skip a couple of slides and finish with the wavefront sensing part by just showing what is the future of this. So now, in order to go on Sky and be able to cope with variations in the system, because we do think that, of course, the atmosphere is variable, but also the status of the system will change over time. One of the things that we are exploring now is to use a technique called reinforcement learning, in which case we continue to learn as we operate the system. And the idea is that there is an agent that makes decision based on a reward. And so we define a reward, which can be typically the quality of the images that we get in the focal plane. And we have a couple of neural networks, one of them that tries to simulate the dynamics of the system, so the response of the system, and another one that tries to define what are the best actions for the agent to take in order to maximize the reward. And so we continue as we operate the instrument to learn and to improve the correction. And that's a project that we are starting together with colleagues at ESO. Okay, moving on now to software performance of image processing. And so this is a work that was started by Carlos Gomez, who was a PhD student in Liège around 2016, and then followed by Carles Cantero, and all that in collaboration with Mark van der Zogenboek, who is a signal processing professor in Liège. So one of the reasons I've introduced the different steps of high-contrast imaging is because I need this for you to understand what follows. And going further than just measuring the images and taking the median as our model for the response of the telescope, we can do better. And usually what is done these days is to use principal and component analysis. So you basically use principal component analysis to reduce the dimensionality of your data set here, and you project your images onto the first few principal components that are expected to capture the behavior of the stellar PSF. Okay, and so once you do that, you form a model for your stellar PSF. You can subtract it from each individual frame, so you have a model that is now matched to each single frame. You subtract, you derivate, and you combine. So that's still the same principle. So what I want to highlight now is that when you are left with the final frame, so the final step in your image processing, you get a frame where you have potentially a bright blob, but you still have to find a way to tell whether this is significant or not. So usually what you do in order to test whether this blob of light is significant or not is to use a two-sample t-test, where you compare the amount of flux in a little aperture around this bright blob to the standard deviation of the flux in all the apertures at the same angular separation from the star. And the reason why you do that, it's because you know that the behavior of the noise is radially dependent, with more noise close to the star, where the speckles are brighter, and less noise towards the other part of the system, where you are starting to be more and more dominated by background noise. Okay, so the behavior of the noise changes radially. So here, if you compare the signal of this little aperture here to the noise and the standard deviation of the other apertures, and you get a value of 7.8 or 7.0, well, you can say probably I have something significant. The problem is that this presupposes that you know the statistics of your noise. And typically what you do is to make Gaussian assumption that the noise should behave more or less Gaussian, but it's usually not the case, especially close to the star. And even more than that, when you are close to the star, you have a very limited number of test apertures, which means that you are limited by small sample statistics, which reduces even more the significance of your detection. So here, having a signal-to-noise ratio of 7 doesn't mean that your detection is significant. So one of the things that are done in the community to try to figure out whether a signal is real or not is to plot the evolution of the signal-to-noise ratio as a function of the number of principal components that are used in the modeling of a PSF. So if you are using very few principal components, that means that you do not capture very well the behavior of the stellar speckles. So that means that you do not subtract the noise very well. And so as you increase the number of components, you subtract the noise better and better, and you increase your signal-to-noise ratio. But at some point, when you are using too many principal components, you start to capture the planet inside your principal component basis, which means that when you use too many components, you start self-subtracting the planetary signal, and you start losing signal-to-noise ratio again. And so this shape of the signal-to-noise ratio curve is really the tug of war between you making a better job modeling the noise and you starting to subtract the signal that you want to detect. So now, how does machine learning fit in this context? Well, the problem is that we only have like a dozen planets or so that we know of. So we do not have like a big label data set that we can use to teach a machine to recognize the planets. So we have to resort to creating synthetic images. And what we do is not really creating synthetic images, just to inject fake companions into real images. So we use images that are taken in the telescope where we think there is no planet present, and we inject planets following the appropriate trajectory that are linked to the field rotation. And so from that, we can create a big data set with a lot of fake companions injected one by one in these data sets. The problem is now to train your neural network. And if you look at the data, even after PC processing, you usually are left with this kind of images here, where it's very hard to disentangle what is noise and what is not noise. And so even a human eye would have a very hard time putting labels on these structures. So definitely this is not what we do. And we are using tricks in order for the machine to be able to recognize the pattern that follows signal compared to noise. And for that, we use several tricks. I will not go into the details of that, but basically what we do is to separate the field of view in little patches and to produce images with different number of principal components. And so I'm showing here what happens in a part of the field of view where we did not inject any planets. So these are different little patches, like 2x2 resolution elements that are cropped out of the final images after PC processing. And so you see that depending on the number of principal components, so these are the number of principal components that were used to model the stellar PSF, the shape of the noise will change because as you increase the number of components, you subtract the noise better and better. While in the samples where we have injected planets, you see that the shape of the signal remains more or less constant because the planet is there, and whatever we do, I mean, of course, the contribution of noise changes as you increase the number of principal components, and you start decreasing, self-subtracting a little bit the planetary signal, but you see that the shape and the behavior of the signal versus the number of principal components is very different when you have injected the planet than when you only have noise. And while when you compare some of these samples, they can look very much alike. It's really the behavior as a function of the number of principal components that will tell you whether it's a true signal or whether it's noise. And that's something that the machine can pick up. So what we do is from a large number of these kind of samples to train a classifier that will just try to recognize between the class C+, where planets were injected, and the class C-, where planets were not injected. Okay, and so the architecture that we use to do that, once again, is based on the convolutional neural network, because these are the kind of networks that do handle 2D images and the structure of 2D images. But on top of that, we use a different kind of network. We combine that with a different kind of network that is called long short-term memory network. These are networks that are usually used to capture temporal behaviors in systems, except that here, instead of time, we are using the number of principal components as our variable where the behavior of the data needs to be captured. And this is where we started writing the hype curve with our innovation trigger. And so we tried this on different data sets. And so you see here the famous HR799 data set with the 4 planets. This is the standard processing of this data. This is the processing with our neural network called SODIN, where we get basically a probability. So the classifier is giving you a probability of belonging either to the C+ class or the C- class. And typically what you do is to threshold this map in order to tell whether something is a detection or not. And it seems to work quite well. And even better than that, when we did a lot of injection and recovery tests, we tried to compute the true positive rate, so how many of the injections we could recover. We computed the number of false positives, and we figured out that our classifier here was towards the upper left, the oracle where we would like to be. So this would be the perfect classifier that would tell all the true positives without having any false positive. And these are the curves of more standard techniques like PCA. So we were quite happy and impressed, and this is where we started to go up the high curve towards the peak of inflated expectations. As you can imagine, something happened, and what happened is the exoplanet imaging data challenge. So this is a community-wide challenge that we organized in order to try to compare the merits of different image processing algorithms. So there's a whole big zoo of image processing algorithms. And the bottom line is that our neural network classifier did a very good job retrieving all the planets that were injected in the data, but also created a lot of false positives. And we were not expecting that. And that was a big setback in the for us, and that's where we went down to the trough of disillusionment. So, but still, using this data challenge, we could learn some lessons, and one of them is that image processing techniques that were using that were working locally were doing a better job, and it is not very surprising because of the fact that the noise has this radial dependence. If you could train a network to recognize the speckled noise at the center and to be more adapted to background noise in the other part of the field of view, you think that you can gain something. So this is one of the things we did. So train different neural networks for different parts of the field of view, trying to recognize the statistics of the noise and separate the field of view in different parts depending on the noise statistics. So another thing that we did is to add more handcrafted features to the neural network. And so one of the things that we injected is this signal-to-noise ratio curve that I was showing before. So as a function of the number of principal components, you can measure the signal-to-noise ratio for any pixel in your field of view. And you see that if you have signal or if you have noise, these curves have very different behavior, as I was already mentioning before. And so this is something that was not really captured with our images versus a number of principal components, because it was just capturing the shape, but not really the signal-to-noise ratio, because signal-to-noise ratio depends also on the surrounding apertures. So in addition to presenting just the images, we also presented these curves to the neural network. And I guess this is the busiest plot of my presentation, but just to highlight a couple of things. So we still create these two classes, C+ and C-, that we inject in our neural network to train it. But at the output of the neural network, we add the information about the SNR curves before the final layer that produces the prediction. On top of that, we separate now the field of view in different regions, a region where we think that the noise is dominated by residual stellar light, and a region that is more dominated by background noise. And when we do that, lo and behold, everything seems to be working better, and we submitted a new entry in the data challenge, and we are now at pretty much the top of the leaderboard, where all the false positives have now disappeared by using this double trick of separating the field of view in different regions and inputting more handcrafted feature and more knowledge to the neural network. And so we brought up the slope of enlightenment, and we are now finally reaching the plateau of productivity, where unfortunately I cannot show you much result yet. We are still in the process of trying to reprocess some archival data and try to look for fainter companions, facing new challenges now, which is mostly the fact that because these techniques are so sensitive, that they produce new detections that we cannot really vet compared to other techniques. And we will have to go back to the telescope to confirm that these companions are real.
Are you going to explain a bit how you could get uncertainties on the detections?
I can come back on that during the question. Okay, so I want to finish within 5 minutes or so with the last application, which is improving the scientific exploitation of extracted spectra. So this is a work that's done in collaboration with Gilles, once also a professor in computer science department. And so at the end of the day, when you extract a spectrum from your observation, what you usually do is to use Bayesian sampling methods, so Bayesian inference, in order to try to constrain the parameters of a model. So you have your observation, you compute a likelihood by comparing that to some kind of simulations, and then you loop that and you update your priors in order for the likelihood to be maximized. And so this is a an iterative method that requires a lot of calls to the simulator in order to explore the parameter space and converge towards the most probable value for your model parameters. So the problem with Bayesian sampling methods is that, as I said, it's sequential. So that means that you need a series of calls to a potentially complex simulator, and especially if you have a very complex simulator of planetary atmosphere here, it can be quite expensive to each step of your sampling algorithm. And also the fact that these methods are usually struggling with high-dimensional parameter space. So this is the curse of dimensionality. When you are starting to have 20, 30, 40 parameters, it's starting to be hard to exhaustively explore the parameter space. So machine learning can be used and has been used already in the past to try to solve some of these issues. So in the past, two things that had been done is either train a neural network to try to retrieve the model parameters directly, or to aid the standard Bayesian sampling techniques with ML tools by, for instance, replacing your simulator by a surrogate neural network that would produce simulations faster. But what we do is going a little bit further, and it's trying to train a neural network to directly output the posterior distribution for your model parameters. And so the way you do that is the following. So I will try to briefly, explain how this goes. So you have, generate parameters from your prior, you pass that through your simulator to create simulated observations, and then you will train a neural network that will try to map these couples of parameters and observations towards directly a posterior distribution. So the way you do that is using a mathematical trick where you can show that you can re-express, reformulate the expectancy of the distance between the true posterior distribution and your parametric posterior distribution in a way that only depends on this parametric posterior distribution. And so you have here the expected value depending on the joint probability of model parameters and spectra of your parametric probability. So for that to work, you need to find a way for a neural network to be able to spit out probability distribution, and this is something that is typically done by normalizing flows that basically match standard distribution like Gaussians towards more complex distribution in an invertible way. And so you can basically, by generating a lot of couples of x and theta, so observations and or simulations and model parameters, you can train your network to predict the posterior distribution for your model parameters. And so when you are doing inference, what you do is just take your observation, pass it through the neural network. And so you basically condition your neural network to the observation for it to output what it thinks is the posterior distribution for the model parameters linked to that particular observation. And so the main advantages of that kind of technique is that it produces accurate posteriors. So you do not make any assumption on the shape of the posterior like most machine learning techniques used to do before this kind of technique came up. It is fast, amortized, so that means that once you have trained the network, so you spend a lot of resources to train the network, once it's trained, you can make instantaneous inference. So that means it takes only a couple of seconds to produce the posteriors based on a new observation that is shown to the network. It is scalable and it's testable. And testable, I will come back on that. But first, I just want to highlight the fact that we tried this network, we tested it against sampling methods. And well, this is the case here of one of the exoplanets of the HR8799 system, where we trained a model using 20 or more parameters. Here I only show a few of them, just to highlight the fact that the posterior distributions from our neural posterior estimator are quite similar to the multi-nest, so nested sampling retrieval. Although you see that there are some differences, and in particular, you can see that the NPO posteriors tend to be a little bit broader than the nested sampling posteriors. And this is something that not only us see, but many other teams that are using machine learning-based inference techniques do see that nested sampling tends to produce narrow posteriors compared to machine learning methods. So now, important point here is the time it takes. So when you do nested sampling on this kind of complex data set with many full spectrum of a planet and a complex model, it takes several, typically 100 hours, while for NPE, it takes 17 hours to generate the data, 13 hours to train on the standard GPU, and only 10 seconds to do inference, which means that anytime you have a new observation that matches the model that you have trained, it only takes 10 seconds for you to produce the posterior distributions. I'm going to finish with this to highlight an important point of amortization and the fact that you can do instantaneous inference is the fact that you can now test the quality of your posteriors. And one of the, what you can do, of course, is draw random samples from your posterior. That's something that you can already do with other techniques. But this is more important here. This is what we call a coverage plot. And basically what we do here is that we create a lot of synthetic data. We retrieve on them, and we look whether the true parameters are contained within the 50% credible interval 50% of the time. If it's the case, we are along this diagonal here. That means that your posterior is well calibrated. If the true parameters of your observation fall within the 50% credible interval only 10% of the time, that means that you have overestimated the width of your posterior. So you are under dispersed, so that means that your posteriors are too wide, or the other way around. If your true parameters fall into your 50% credible interval more than 50% of the time. So we can really test whether our posteriors are well calibrated. This is not something that you can do with nested sampling, just because this relies on repeating the inference many times on synthetic data, which is something that would take like 100 hours to do for any additional observation with nested sampling. Okay, so coming to my conclusions. So I hope I have convinced you that despite the fact that high contrast imaging is becoming a mature technique, there is still a lot we can do with current instruments, both in trying to improve their operations, but also getting more out of the data that they acquire. There are even more opportunities of using machine learning in the field of high contrast imaging, which I didn't have time to cover today. In particular, regarding adaptive optics control. So reinforcement learning is now a technique that is starting to be deployed on adaptive optics systems. You can also use machine learning to help in the way you design the coronagraph itself. But I cannot finish without mentioning that there are, of course, several challenges in trying to deploy machine learning techniques in a field like high contrast imaging, but many other fields. Is first, the way you formulate the problem is very key. So trying to reformulate the problem in a way that it can be answered by machine learning techniques is very important. And this is the very first step that you have to take. Finding the right machine learning tools and especially keeping up with the exponential progress in machine learning is quite a challenge. And finally, once you have trained your system, you still have to rely on some kind of black boxy behavior. And you have to make sure that the model that you have trained is sufficiently general and interpretable so that you can make informed science from the output of your ML model. And I'm going to stop here. Thank you.
Thank you, Olivier, for this nice presentation. We usually say to the large public that direct imaging is just taking a picture of a planet and the star, but it's quite more complex. So, other questions? Sorry, yes.
Very impressive. Why do you still have a PCA in there? The PCA is basically to do the PSF modeling.
Yeah.
It's kind of funny to use this old technique with like all this super duper machine learning stuff. So you must have looked at ways to get rid of that.
Yeah. So the reason why we did, okay. So first we started just trying to input raw data to the ML model, and it was complete failure. So the reason for that is that the dynamic range in this raw data is just so huge that it's impossible for the machine to pick up the very faint signal that is in this. So we had to pre-process the data in a way that the machine can figure out the behavior of the true signal compared to the noise. So, yeah.
Processing is half of the work, in fact.
Yeah.
Are there more questions? Other questions? I have one question. You have shown in the different algorithm, and how many use deep learning in this? Because the Loki algorithm is quite it's a very old algorithm. It's just some mathematics. So what are the different ingredients compared to what you are doing?
Yeah, well, I mean, models like PCA can also be, considered as machine learning because at the end of the day, you are using data, you are building a model from your data. This is not so different from, the field of machine learning. It's just that in that case, it's a pure linear model. What the machine learning brings you is a non-linearity. And this is something that can be quite useful because you know that spectral noise is something that is not linear. I mean, it's more complex than just a linear model for the noise. So yeah.
So all the competitors are also this kind of machine learning tools, some extent.
There are not so well. So there are many linear models for spectral subtraction, PSF modeling around. There are also people that use inverse problems, that formulation that are also usually making some assumption on the noise or on the fact that the problem is linear or something like that. There are not so many groups that are really using machine learning in terms of like deep networks. I know of a couple other groups that do investigate this kind of techniques, and it shows promise. But as I said, at the end of the day, when you get the result of your experiment, you still have to find a way to convince yourself that this is real. And so you can make all the fake injections of the world. You know that the true signal is never going to be exactly what your fake injection looks like. And so you have to convince yourself that it is true. And the only way to do that is to go back to the telescope and confirm that your companions are still there. And this is something that we are in the process of trying to do.
Are there more questions? Yes, Florent?
I'm not in the field of exoplanets, but I can ask maybe a question about the deep learning part. So in this application where you had an autoencoder and the decoder and the Zernike polynomials as the latent space, well, two-part question. First, how many coefficients do you use to correctly describe your image? And you've had to assume that, I guess, the Zernike polynomial is the right basis to do that, but maybe you could have actually a machine which discovers itself the latent space.
Yes, indeed. So maybe I will briefly come back to that slide. So first, we know that for optical systems and even for atmospheric bubbles, the Zernike modes are a sound basis to describe the behavior of aberrations. So that's one thing. The other thing is that if we want to be able to use a physical model as a decoder, we need to know the physical meaning of the latent space. And so this is why we stick to Zernike coefficients, because they are very easy to handle in an optical simulator. So that's the reason. We really force this latent space to have a physical meaning that we understand, because at the end of the day, we will use that to do the correction as well. So yeah, but you are right that we could use other bases, and there are actually there might be some reasons to use other bases for specific applications, but yeah.
How many coefficients do you?
Oh yeah. So
with respect to the dimension.
Yeah. So typically we are using up to 100 coefficients, and this is more or less where we start struggling to learn more. Yeah. So as you go to higher and higher Zernike modes, the aberrations start to be like more and more localized and harder to map from your focal plane images.
Yes.
Yeah, can we come back to the high contrast image that you showed at the very beginning, where you had a signal of 7.8 or something like that?
Oh, yeah.
Yeah, you see?
Sorry. Yeah.
Before that, I guess.
Must be here.
Yes. So is that a detection? You detect something, you call it a planet, and you want to compare the signal to noise with other aperture?
Yeah. So this one is a true planet, and this one is not. The problem is that when you look at the significance of the detection, if you compare the signal to the noise, they are of the same order, right? So which means that we are facing a problem here. That's just this simple value of the signal-to-noise ratio is not enough for you to vet the nature of the candidate signal. So in general, when you process data, you see several blobs that are typically can be either speculators that have not been properly subtracted or can be true signal. And you have to compute this signal-to-noise ratio for you to decide whether this is significant or whether this is rather part of the noise.
Yeah, but I was confused because you choose aperture which design a circle,
Yes.
but it has nothing to do with the real orbit of the
Oh,
planet.
no, it has nothing to do. It's just because the fact that the noise has this radial dependence, so we want to compare the signals to the noise in the region where the noise is supposed to be the same as for that particular element.
But by the way, another question which is related to that, not to the observations, but how many orbits are we able to measure now in exoplanets? In other words, what is the proportion of circular orbits with respect to non-circular orbits, elliptical ones?
Okay, well, I guess
You know, this is not related to.
yeah, that pertains more to radial velocities and methods. There is a large diversity of orbits. But still, most of the eccentricities are usually low. So the number of planets that are known to have high eccentricity are still relatively few. We do know a few cases where the eccentricity is large. We even know cases where there are some systems that have non-complanar planets, so which typically are telling you that there have been some dynamical interactions with the planet. They have sent one of them on a highly eccentric and inclined orbit, but these are only few. Most of the planets have orbits that are close to circular or at least low eccentricity.
Because about 10 years ago, it was claimed the contrary, that the circular orbits were exceptional, and most of them were highly elliptical.
No.
I read that book. Thank you.
Well, there is eccentricity, of course. But not super high eccentricity. These are still relatively few.
Their last question. Okay, so thank you again, Olivier.